Section 4.6 is our last section of material that we're going to do in Chapter 4. There is one more section. We're going to stop with 4.6. And in this section of material, we're going to talk about one of the ways that we can end up being able to handle things that look like products. Now, you've already sort of dealt with one of the ways before. That is, you can somehow simplify the product either with a trig identity, perhaps, or maybe by multiplying things or dividing them out. This is another option. So we're going to take one. I'm going to show you kind of where this comes from with what you remember about derivatives. Excuse me. So let's take the function y equals sine of x cubed minus 4x, and let's take the derivative of that. So what is the derivative of sine? Cosine. I hope that as you did this, you recognize this is a chain rule. We have something inside of a sine, so we rewrite the inside. And then we take the derivative of the inside. And what is the derivative of the inside of this one?
3x squared minus 4.
Good. So this is what we have, what it ends up looking like. And it looks like a product, right? This is a product. Now what we're going to do is we're going to consider going to in reverse. That is, let's say we started with what it looked like a product, and it looked like this product. And we wanted to go the backwards direction. So you can take this function, and there's some difficulties in doing this in general because it looks like a product. So if you just started with this expression prior to class today, you would have sort of been stuck. It looks like a product. It doesn't simplify with algebra. It doesn't simplify with trig either. There's no identities to handle it. What do we do? Because it looks like a product. Well, not only does it look like a product, it really is a product. It's just that because it's a product in the way that it's shaped or because of the way it was formed, it's still able to be handled. So let me show you how we handle a product like that. So one option when we're presented with finding an antiderivative that looks like a product is to decide if there's a composite function. So the idea is that it's a composite function present for which the inside function's derivative is one of the factors being multiplied. Now, there's nothing to fill in there, but so let me go back over here and identify for you what I mean. Well, this particular portion of the product is the derivative of what lies inside the other portion. Can you see that? I mean, that's how we created it, right? Now, we're going to start with functions where we didn't create it to do that, but it still has that feature. What's inside still looks like its derivative is the other piece of what's being multiplied. So if we consider the y prime above, 4 cubed minus 4x, x cubed minus 4x is an inside function. Its derivative, 3x squared minus 4, is one of the factors being multiplied. And this is the way that we handle it then when we're working with antiderivatives. We let u equal the inside function, so x cubed minus 4x. And then we take the derivative, and I know I'm going to write it in a notation that we've not used a lot, but I'll show you why I want it in a minute. So one way of taking the derivative of the function u is to write it as du dx, like with implicit differentiation, right? We saw it there. What is the derivative of x cubed minus 4x? It's not a trick question.
3x squared minus 4.
Thank you, 3x squared minus 4. And the way that we're actually going to write it is not the way I just wrote it. Instead, we're going to write this as du equals 3x squared minus 4 dx. We'll put this in parentheses just to indicate the multiplication is really happening to both pieces. So if you go from this left-hand expression here to this right-hand expression, what did I do? Yeah, I just moved the dx. I multiplied by dx on both sides. So I want to show you how this actually works in practice. So if we started with an integral that started out as the cosine of x cubed minus 4x times 3x squared minus 4 dx. Right? That's what it would have looked like. That's the entire derivative that we created just a moment ago, put in there with the antiderivative notation surrounding it. What we would do is we would identify, let me see, this would have a parentheses here too. We would identify that this piece is u, and so we would write down u equals x cubed minus 4x, and then we would write down that du is 3x squared minus 4 dx. And of course, we're understanding that that dx comes from that du over dx being multiplied to the other side. And then what we do is we do substitution. So we come over here and we say, all right, this piece, u, is equivalent to x cubed minus 4x. So instead of writing cosine of x cubed minus 4x, I'm going to write cosine of u, because they're equivalent. It's just another name for it. And then the 3x squared minus 4, this piece, dx, is equivalent to du. So it gets replaced, all of that, with du. Okay? We're doing a glorified substitution. It's called u substitution because we're using the letter u as our substitution variable. Okay? The reason that we did that is because that's a very simple antiderivative. You can do that. There's no products. There's nothing messy at all with it. So what is the antiderivative of cosine of u? It's positive. Positive sine of u. Okay? Now, that can't be my answer. Why can't that be my final answer? Because there's a u in it. And I started the problem with x in it. It's kind of like what we've been working with in some other areas where I say, if it started out with square roots, I'm not going to have, powers of fractional powers in the answer, right? I want it to look like what it started out looking like. This started out with x's in it. The answer needs to have x's in it. So we do a back substituting step at the very end, and we say that this is the sine. I need a plus c here too, sorry. This is the sine of x cubed minus 4x, because that's what u equaled, plus the constant c. And that would be my final answer. And now that should make sense because that's actually where we started the problem. Right? We started the problem with the function y equals sine of x cubed minus 4x. And then, of course, as we've talked about, that plus c because we could have the function shifted up or down and not change the derivative value. So that's why that plus c is there. That's the process we're going to do for all of these. But that's where it came from. It came from the idea of chain rules. Okay, it came from the idea of a composite function with a chain rule present. Okay, you guys ready to try some now? But that's how we're going to process through these. All right, this says find the indefinite integral. And it says that we've got the integral of the cube root of 3 minus 4x squared times negative 8x. So it looks like a product, agreed? I've got two different pieces. They both have x in it. If I were doing derivatives, I'd have to use a product rule, but I'm not. I'm doing antiderivatives. So what we want to do is we want to identify what looks like it's inside of something else. So what looks like it's inside of something else? Yeah. It's inside of a cube root, right, Zach? Yeah. All right, so the u here is going to be that very thing, 3 minus 4x squared. Then I would write down du. I need to take the derivative of 3 minus 4x squared, and I realized that that means I'm doing a derivative in the middle of an antiderivative. So you have to be very careful that you're thinking of the right one. What is the derivative of this u? Negative 8x. And is that a good thing, Brooks? It is a good thing, actually. Why would I think it's a good thing? What do you think, Tyler?
Because negative 8x is multiplied.
Yeah, because there's a negative 8x in my problem. That's why it's a good thing. That piece is exactly what I wanted it to be. It's the other piece of the product. Now, it's not just negative 8x. It's actually negative 8x dx. All of this is right here that I just underlined in the black. That's going to be replaced by du. The part that's underlined in green is going to be replaced by the letter u. So this actually ends up becoming the cube root, or sorry, the integral of the cube root of u du. It's a substitution step that simplifies the process. Now, there's probably one more thing we'd like to do is that we'd write that u to the 1/3 to take its antiderivative. All right, so what is the antiderivative of u to the 1/3? Okay, so the u is to the 4/3, and then what do? Over 4/3. We need a plus c at the end, of course. And then division by 4/3 is the same as multiplication by 3/4. The 4/3 as a fractional exponent is a cube root of u to the fourth. Right, it started out with a cube root in it. It's going to end with that cube root notation in it. But I need to replace the u with what u actually equaled in terms of x's. So this is the cube root of 3 minus 4x squared. Okay, sorry. There we go. And then to the fourth power plus the c. What do you think? Is that one okay? Any questions before you go to the next one? Okay. This one looks a little different because it doesn't actually look like a product. It looks like a quotient, right? But it can't be handled the way that we've been doing the quotients that we have been able to handle because the addition or subtraction is actually in the denominator on this one, right? That's why what we've been doing with our simplification won't work here. The ones we've been doing had addition and subtraction on top. This one has it on bottom. But there is the idea, a product is just the same as a quotient. It just ends up being a quotient with the part. If I wanted to make it look like a product, I could take what's in the denominator and move it up with a negative exponent so that it actually looked like product. So product and a quotient are equivalent ideas. So u substitution is still appropriate here. What looks like it's inside of something else? Yeah, the 1 plus x to the fourth. So that's where we're going to start. And of course, if you start with something that doesn't work, you can always go back and try something else. So there's really no problem if you make a mistake. It didn't work on this one. We try something different if you've identified it wrong. It might, in fact, have been nice to actually let the entire denominator be u, right? I mean, that would have been a possibility. It doesn't work on this one, but it could have worked. Now, this one looks like the denominator, the part that's inside the parentheses, is actually my inside function, and it really works. It works a little different, though. This is why I chose this one. What would the du be on this?
4x cubed.
4x cubed dx. Why do I say that's a little bit different than the last one? What's different about it?
You have a constant that doesn't match up.
Right. That 4 in the front is not in the problem currently, is it? No. So I'm going to show you one way to deal with it. I have found this to be the most helpful. There's other ways to do it too. So this piece right here matches up, to use Tyler's phrasing, right? It matches up to what we have. It's right here. So let's just move the 4 to the other side with division, okay? So I could rewrite this as 1/4 du, and 1/4 du actually equals x cubed dx. Agreed? It's just some algebra. So why is that helpful? Well, that means I could take the original problem, and the part that I circled in red will be replaced, but it will be replaced with 1/4 du instead of just with du, because those are the two statements that are equivalent now. So I've still got my integral. It's just that I've got a 1/4 du to replace the x cubed dx. And then in the denominator, I've got that u, and that u is still squared because there was a squared right there. Now the notation for this looks a little weird. So I'm a much bigger fan of bringing that 1/4 to the front, and we had learned earlier on that we can do that. If there's a constant, we can pull it into the front of the integral. That was something that we learned way back in, I think, 4.2 maybe, or 4.4, something like that. It's been a little while, but we've learned that fact before. That leaves 1 on the top, u squared on the bottom, du. And it might actually be more helpful to write this as u to the negative 2 instead. So 1/4 of the integral u to the negative 2. All right, so the 1/4 is part of your notation. You're done. What is the antiderivative of u to the negative 2? Close. It's negative 1. We have to add an exponent, add the number 1, but we're starting out with a negative. So when we do negative 2 plus 1, we actually get negative 1 instead of negative 3. Yeah. So this is negative 1. Here's my plus c. So we'll simplify this. This is negative 1 over 4u. plus c. And the u is 1 plus x to the 4th. If you really want to distribute that 4 through, since there's no exponent outside those parentheses, you could. It doesn't really make any difference in the final answer. It's not any more simplified or less simplified. In some ways of thinking, having in that sort of factored form is a more simplified look. So it's perfectly fine to do either one. Now let's say for a moment you're in the middle of the test and you end up with some extra time and you want to make sure that you did the problem right. You want to know, is this really the right answer to this problem? What could you do to make sure that you found the right antiderivative? Take the derivative, right? And then there's nothing special about u substitution that makes that possible. Anything you can do that with, right? So if you want to make sure you've done the antiderivative correctly, take the derivative. If you did it correctly, you should end up with what you started with simplified when you're done. All right? All right, let's take a look at another one. All right, this is an integral with some trig in it, isn't it? You guys like trig. I know, you pretend like you don't, but I know that you kind of like it. No. Well, some of you are shaking your head yes, and some of you are shaking your head no. So some of you like it. There aren't any parentheses on this one. There have been on the last two problems, or at least on the last problem and the one before had sort of an inherent parentheses. There's an inherent parentheses here as well. Where are the parentheses that are sort of not drawn in? Around the which one? The x to the 4th. One way to think about inside-outside functions, and we did this back with chain rule already before, is if you were putting this in your calculator, where would your calculator force parentheses to be? Well, they would put some parentheses around that angle. And so there are some parentheses there. And sometimes drawing them in, like we just did, makes it easier to identify inside functions. So what's the inside function on this one? It's x to the 4th. And what is the derivative of that? 4x cubed dx, right? All right, so there is a 4x cubed and there is a dx. They're sort of separated. But, I mean, like if we just did some commutativity, right, just move things around, they'd be together. So the part that's underlined in green, all of that is going to get replaced by the du. So here's du, also in green. The sign doesn't get replaced. It's still there, so there's sign. And the part that's in red is u, so this is u. So this is sine of u du. Excellent. What is the antiderivative of sine? It is negative cosine. Yes, it is. Very good. Of u, and then plus c. All of that. Not finished because there's a u in it, so I've got negative cosine of what? X to the 4th. And then plus c. If you want to put the parentheses around the x to the 4th, kind of like we put them in red to begin with, that's fine. If you want to leave them off, that's fine too. So this is your final answer on that one. Is that okay? All right, there's another trig one next. And this one is much less obvious what the inside function should be. But it definitely looks like a quotient, aka a product, right? I mean, we could think of it as a product. What do you think you could let, I mean, you only have two options. What could you let u be? You could let u be x. The problem with letting u be x is it doesn't simplify anything. You're just turning u's into x's. It doesn't actually change the problem. So that's called a trivial substitution that doesn't ever really help you out. So we kind of want to avoid that one. I hadn't thought to mention that, so I'm glad that somebody mentioned that one. So what else could we let u be? Okay, you could let u be either sine of x or cosine of x. And in fact, that's a really good train of thinking to be along because they're each other's derivatives, right? So if you put one of them as one thing, then the other piece is going to be there automatically with the derivative when you take the derivative. So the question is, which one do we want to use as u? We want to use cosine. Do you know why, Micaiah? It's not because it's positive, although that's not a bad thing that we're going to have happen here. There's another reason. It's in the denominator. Yeah. We want to let whatever be in the denominator when we have that option work out, because when we take the derivative, we're going to get it to be times du, not with something in a denominator. We don't want the du in the denominator. The du needs to be outside, in the numerator, if you will. So we're going to let our denominator, in this case, just the cosine part, be u. So what then is the derivative? What's the derivative of cosine? That is actually negative sine x dx. And there's not a negative in the problem right now, is there? So we're going to treat it much like I did on the earlier problem, where I'm going to bring the negative over to here. So all of this sine x dx piece is going to be replaced with a negative, which I'll just put in the front, and a du. There's a 1 on top now because I replaced everything else. U is cosine, but that's not what's in the denominator. And the denominator is cosine cubed. So what are we going to put in our denominator now? U cubed, right. So this will be negative the integral of u to the negative 3 du. Okay, so here's the negative. What is the antiderivative of u to the negative 3? U to the negative 2 over negative 2, and then plus c. All right, so many of you are already really good at doing this, but the negatives cancel, right? You guys keep even doing it on your quiz where you don't have to simplify anything. So I don't have any negatives. I can write a 1 on top. There's now a 2 in the denominator, and that u to the negative 2 can be brought back down to the denominator as u squared, and then plus c. Is that stuff okay? Oh, it didn't show up on there. All right, that's all right. We'll get it to show up. Uh-huh.
Can you explain what that is?
Yeah, I mean, basically what you're doing is you're replacing, this is like negative 1. You've multiplied by negative 1 on the other side. So I've pulled the negative out in front as a negative or a negative 1. And then the numerator could be, I mean, I could write the du up here if I wanted to.
Okay.
I just like to see the du's at the back. I mean, I always put my du at the end.
Since du is sine and the numerator is sine, is that why you can?
Yes.
You just factor it out.
Exactly.
Okay.
Mm-hmm.
That makes sense.
So you can always put an arbitrary, not an arbitrary, but an understood 1 in a place where there is a quantity that you've replaced like that. And it's the same kind of idea. Some of you have seen that happen on some of your basic skills quizzes where the piece simply doesn't look like it's there and there's really a 1 there. That kind of stuff. Same things happen.
What if your numerator didn't match up with the du? Do you still rewrite the numerator?
If the numerator's not going to match up with the du completely,
Does that mean you did it
you
wrong?
couldn't use u substitution, or you made a mistake in trying to do so. Yeah. So with the exception of being able to multiply or divide something to the other side, like we've been doing over here, like on this one with the negative 1 du over here, with the exception of that, when you're working with u substitution, everything will simplify. Okay? You may have an extra constant or something like that. That's not a problem. But all the pieces that look like multiplication will simplify. Yeah. Am I done? Not quite. I still need to replace that u, right? So this is 1 over 2. And u is actually cosine. So cosine squared, which we usually leave written like this, but if you put it in parentheses with the squared on the outside, that's okay too. And then plus my c. Any questions? Okay, what's different about the very last problem? Or it's not the very last problem. I guess the next problem, I'm sorry. There's what? There's a 9 and a 1. And in fact, the directions also change then, and they say to find the definite integral. So definite integrals occur when we have limits of integration on the top and the bottom. There's multiple ways to handle limits of integration. I'm going to show you the one that's the simplest, and then I'll talk through the other one if you were to want to do it. Okay? Sound good? All right. The simplest way to do your limits of integration when you're working with u substitution like we are is to simply ignore them for the moment. Right? you've got a problem, you're just going to ignore it for the moment. We have a problem, and we're going to ignore it until we can actually deal with it. So we're going to treat the problem as though those limits weren't there. Now, this one looks kind of messy, doesn't it? I've got a square root of x, and I've got a parentheses around 1 plus square root of x. All that's written to the power of 2. It's both pieces in the denominator. Yuck. But we can do it. Any ideas about what your inside function should be?
1 plus square root of x.
Yeah, it looks like it's inside a set of parentheses, right? So it's a good place to start, even if you weren't sure that that was going to work. That would be a reasonable starting point. All right, so we're going to say that u is equal to the 1 plus the square root of x, the part that's inside this parenthesis. Now, as you're taking a derivative, as we did before, you might think of it like this instead, right? 1 plus x to the 1/2. All right, so what will the derivative of u be? Good, and dx, right? All right, so I'm going to rewrite this a little bit. The 1/2 is clearly not in the problem, yeah? So there's definitely not a 1/2 in this problem as it was originally written. Agreed? So what I'm going to do with the 1/2 is I'm going to multiply to the other side. Or I'm going to divide the other side by 1/2, but that's the same as multiplying both sides by 2. Okay, so I'm going to multiply both sides by 2, which gives me 2 du on the left, and the 1/2 will go away on the right. How else could I write x to the negative 1/2? 1 over x square rooted, or square root of x, right? Do you almost see that in your problem now? It still looks a little bit funny, but what you want to recognize is that you could write this like this. I'm sorry, that square root's not supposed to be there. Here we go. We don't usually think about separating fractions like that, but it's true. It works, right? So this piece right here and this piece are the piece that are missing down here. There's that dx. Sorry about that. So all the part that's in red is going to get replaced with a 2 in the front and a du in the back. So I've got 2 in the front. I've got du in the back. And then I've got this integral. The integral is 1 over what? Can you make the substitution? What should it be?
Is it ud?
Well, there is a u in the denominator. Is it only u in the denominator?
U squared.
It is u squared. U is supposed to equal 1 plus square root of x. That's this piece. That's this piece. But that quantity is squared. So in the denominator, I have that same quantity, which we're now calling u, and I have it squared. So I'm going to take this, I'm going to rewrite it one more time before we deal with it. This is u. I'm sorry, this is 2 times the integral of u to the negative 2 du. Okay, is everybody good with that step? The rewriting step? What's the antiderivative here? Well, the 2 gets to stay put. That's a constant multiplier. We don't have to worry about them. What is the antiderivative of u to the negative 2? Good. So this problem actually ends up being negative 2 over u plus c. I need some more space, so I'm moving it. But u wasn't how the problem started. The problem started with x, isn't it, right? Okay, so I'm going to come over here some more space. This is actually equal to negative 2 over 1 plus square root of x. And then normally we would have plus c. Now I don't actually need any plus c's in this particular problem. Why? it's going to cancel out because I'm actually finding a definite integral. So if you want to go back, we don't really need this piece right here, or here, or here, because we're working with a definite integral. And so at the very end, once I get it put back in terms of x's, then I can evaluate it with the limits of integration. So we ignored them until we needed them at the very end, after the x's are back. Because you see that 9 and that 1, those are values that apply to x, not to u. So they have to actually be used in place of the x's, once the x's are present again. All right, so I'm going to evaluate this with the 9 plugged in. So this is negative 2 over 1 plus the square root of 9 minus negative 2 over 1 plus the square root of 1. Well, I think that this negative and that negative will cancel anyway. What's the square root of 9? Plus 1? 4. So this is negative 2 over 4 plus, I have a 2. Square root of 1 is 1. Plus 1 is 2. So this is 2 over 2. So I actually have negative 1/2 plus the number 1 for a grand total of 1/2. All right, so let me reiterate. The only difference on this problem is the very last step, right? Because what I chose to do is I chose to ignore the numbers at the beginning, act like they weren't there, except that we don't have to do the plus c's because we know they're coming back eventually, okay? Chose to act like the numbers weren't there, and then my very last step at the end was to plug them in. Let me briefly tell you one other way to do the problem, because I know a few of you may take Calc 2, and you may not necessarily take it from someone who does what I just did this way. So let me tell you another option. The other option up here is that when you turned things into u's, right here in this step, is that you could redo the limits of integration with the u's plugged in instead. So here's how you do that. You look at those numbers, 1, and you say, if I plugged the number 1 in to x in this problem where I defined x's and u's in terms of each other, and I said, let x equal 1. You said, okay, I have 1 plus the square root of 1. 1 plus the square root of 1 is the number 2. Yeah, so we would put a 2 then here in the place of where the 1 used to be. And then you'd say you do the same thing. You put the 9 in. So if I put the 9 in the place of the square root of x, where the x is, so I have the square root of 9. The square root of 9 is 3. And 1 plus 3 would be 4. Then you change the problem right here instead. Now, it's messy in the meantime, but I will contend that at the very end it's really nice. Because at the very end, I never have to turn anything back into x's. That's kind of nice. The problem with that is that I don't want you to ever forget on the other problems that you do have to turn them back into x's. It's a catch-22, right? Like, it's more difficult at the beginning, it's easier at the end, but by doing this process, you might actually think that somehow the x's went away, and they didn't really go away. All right, so there's innate problems with this, with what you're doing on the other parts, which is why I don't do it this way. But it is a legitimate way to do the problem. Okay, so if you see a professor do that at some other point in a Calc 2 class or something, it's not wrong, it's just a different way of doing it. Let's do one more problem. We'll do it the same way that we just did the last one so that I'm not going to confuse you again. We have the integral from 0 to pi of the sine of x plus the cosine of 2x. Now, part of this problem you don't need to use substitution for. Which part? Which part of this problem can you do just looking at it? Sine x part, right? You know the antiderivative of sine x. Well, except that you might have a negative in your mind wrong because we still are working on that. But aside from that, you know how to do that, right? So we're going to actually split this into two separate integrals. We're allowed to do that. We've got one integral that goes from 0 to pi of sine x that does not need anything to do with u substitution. The other integral that goes from 0 to pi is the cosine of 2x dx. Now this is the only problem that we've done that does not look like a product. Do you see anything here multiplied? Well, sort of. I mean, you see 2 times x, but it's sort of occurring inside of something else. There's not two different things with x in them multiplied, right? So where is there a chain rule? Where is there, what's going on? Well, let's do the part that we know how to do first, and then we'll come back to the part that's got the u substitution second. All right, so then, what is the antiderivative of sine of x? You've got the negative in there, good. Negative cosine x. And it's going to be evaluated at pi and 0, right? Plus some other stuff. We'll get the plus stuff later. So I've got negative cosine of pi minus the negative cosine of 0. What's the cosine of pi? Negative 1. So this is negative of negative 1. These two negatives cancel to be a positive. There's lots of those going on. Then what's the cosine of 0? Yes, 1. What do I have at the beginning? 2. This is 2. 2 plus something that I haven't found yet. All right, so half the problem I don't have to use u substitution for. That's okay. But the other half of the problem, I do need it. I need it because this says cosine of 2x. Now, let me say real quick, there's another way to handle this. You could find your double angle identities in trig and work with it from that perspective. That's a harder perspective to do it from. I don't want to pull up double angle identities. It's not one that I have memorized. Quotient identities, Pythagorean identities, and reciprocal identities are enough. You don't need any of the other ones at the moment, okay? We don't need to do this with double angles. So how do we do it? Well, here's what we do. We simply let u be that angle that's inside. So then, if u is 2x, what would du be? 2 dx. Is there a 2 in the problem? Not yet. There isn't. But I just have to divide it to the other side. So the dx is going to equal 1/2 du. And I'm going to put the 1/2 on the outside. There's the dx that's going to get replaced by the du with the integral. Okay, so dx gets replaced by the 1/2 du. I put the 1/2 du in the 1/2 in front, and I put the du at the end. But they're both there. I just separated them. In the middle, I have a cosine. A cosine of a what? A 2x right now, but what should it be? Of u right now, because I'm changing them into u's. So 2x is equivalent to u, so I replaced the 2x with the u. So I don't have a 2 in there anymore. Is everybody good? But that just looks like something you know how to do, right? Okay. Now notice the 0 and the pi are not there right now because I've turned them into u's. If you put the 0 and the pi there, it means the 0 and the pi apply to u. And they don't. They apply to x. You have to leave them off if they don't apply to the variable you're using. So we're going to rewrite this. We've got the 1/2. And then what is the antiderivative of cosine of u? Sine of u. Yeah, I know. All right, so this is sine of u. And then we don't need the plus c. Agreed? Why do we not need the plus c? Because it's going to cancel out if I put the numbers in a minute. Anyway, so the problem, of course, though, is that the problem really wasn't supposed to be in terms of u, was it? No. So it was supposed to be in terms of x, and x is actually, or I'm sorry, u is actually 2x. So I want to have this then evaluated at pi and at 0 because now I've got the x back in the problem. I've back substituted. So now I have 1/2 sine of 2 times the x, which is pi, minus 1/2 the sine of 2 times the 0. So I've got 2 at the beginning plus 1/2. What is the sine of 2 pi? That is 0. Minus the 1/2. What is the sine of 2 times 0 or 0? What's the sine of 0? 0. All that work for nothing. Because they're both 0. The answer was the 2 that I originally had before I did all the work for the zeros. But we didn't know that till we got to the end, right? We really didn't. Any questions on that? All right.